Okay, folks, so section 11.4, polar coordinates, part 1, side 2. So in side 2, example 3, we're asked to convert each pair r comma theta to rectangular coordinates. So they're given to us in polar coordinates, and we have to convert back to x comma y. It says use exact values where possible, round approximate values to 2 decimal places. So you'll notice that for each of these examples, I've given you a set of axes. In this case, it's the xy axis, so I'm going to graph this point L, 3 comma pi over 3 on the xy plane. So pi over 3 ends up here somewhere, approximately there. So here's my r of 3 and my angle of pi over 3. So for all of these conversions, we have to remember the following. X equals r cosine theta, and y equals r sine theta. So for this one, we have x equals 3 times the cosine of pi over 3, and that equals 3 times 1/2, which we'll write as 3/2. For the y coordinate, we have 3 times the sine of pi over 3, and that's 3 times root 3 over 2, which equals 3 root 3 over 2. So there's our new xy pair, 3/2 for the x coordinate and 3 root 3 over 2 for the y coordinate. I'm going to go ahead and speed through the rest of these. Hopefully you can keep up. Alright folks, there you have it, 6 different pairs of points in polar coordinates that were converted to rectangular coordinates. And hopefully, with part C, you notice, hey, that's a pretty easy one. Didn't really need to use the r cosine theta or r sine theta. Hopefully you saw the same thing here with this one. If I'm at negative pi as my angle of rotation, that just puts me on the negative x coordinate side. So that's just negative 3 comma 0. Now we're going to do kind of the opposite, reverse process of what we just did. We're going to look at each pair of x comma y coordinates and turn those into r comma theta with the specification that r is greater than or equal to 0, so is theta. That'll just make this easier for us. Okay, so the first one I'm going to do, and these I'm going to talk through a little bit more in the last ones because it's not just a straight formula plug and chug like the previous problems. So if I'm at negative 2, and then if I have an x coordinate of negative 2, and then a y coordinate of 2 root 3, I'm somewhere up to about here, and I'm going to look like that. Now, the r value is simply the square root of x squared plus y squared, so let's do that first. And if r equals negative 2 squared plus 2 root 3 squared, and then I have to take the square root of that. I hope that you can almost work through that one in your head. Negative 2 squared is 4. 2 root 3 squared is 4 times 3, which is 12. So I have 12 plus 4, so that's the square root of 16, and that equals plain old 4. So my r value is 4. Now for theta, I have to be careful when I look at theta. So I've already done some right triangle work here by employing the Pythagorean theorem, but this one I need to be careful. I'm really going to look at this angle alpha, and I'm going to say that theta equals pi minus alpha, and alpha is going to be the inverse tangent of 2 root 3 over 2. Okay, so notice I just took the absolute value of both the x and the y coordinates. The inverse tangent of 2 root 3 over 2, well, that's just the inverse tangent of root 3, and that's going to give me pi over 3. So when I do pi minus pi over 3, that's going to give me 2 pi over 3. So I have my r comma theta, and writing that as an ordered pair would look like this. Now, folks, I'm going to go through the next couple here pretty quickly for you, but I will warn you that some of these get tricky. You can't just do the straight inverse tangent of y over x. You need to think about what quadrant it's in and what the output of the inverse tangent function actually is. And that's it, folks. So we've taken 6 different pairs of points in x, y Cartesian coordinates and turned them into r comma theta coordinates. The one unique thing there that I hope you caught, understood what was going on is when I use this little reference angle alpha, the reference angle alpha will always be the tangent of the absolute value of y over x. So basically you just strip off any negatives from the x and y coordinates, and that gives you an angle in quadrant 1, and I then either adjust pi, so here I subtracted that angle from pi because it was less than pi radians. In this case here in part B, I added that reference angle to pi, so it's pi plus that angle to give me the entire angle theta. And remember, the angle theta is actually this angle here measured in standard position. So I didn't mention that, but it's worth noting. I had another one over here where the reference angle theta, I had to subtract that reference angle from 2 pi because it was an angle in quadrant 4. So again, several different examples there, and this is some of the type of work you'll be expected to do in WebAssign for this section. Good luck to you, folks.